In the last podcast, we talked about how a function could be defined by a formula, and the formula could lead to an infinite set of ordered pairs. If you look at the two functions right here, they clearly represent very different functions. One is y is 2x minus 3, other y is x squared minus x, and yet x is the first number, y is the second number for both of them. So if we were trying to use both together to do something, we could get very confused about what x and what y we were talking about, since there's exactly the same symbols in both. So in this podcast, we're going to introduce a new notation for functions. For instance, instead of calling that first function y, I could call it f of x. Now I want to make something clear. This is not multiplication. This doesn't mean f times x. Y here was just the second number of the ordered pair. So if I made the ordered pair here, the first number would be x, the second number would be f of x. So that f of x is just representing y. This is a single number. It is not multiplication. And to distinguish that from the second one, I could name the second one g of x. And now we could kind of do things in combinations, and we wouldn't be getting confused about which y represented which function. Now, to give an example of that, suppose I ask you to find g of negative 3. You know immediately not to go to this first one because it's the second one that's g. The method for doing that is what I call writing with empty holes. You just write g of anything, put an empty hole for g of x, equals, and each time you come to a variable, put an empty hole. Empty hole squared minus empty hole for x squared minus x. And then if you want g of negative 3, you just put negative 3 into every one of the empty holes. So this is 9 minus negative 3 is plus 3, so that would be 12. Well, that's a pretty simple one. You're just plugging in a negative 3 for x. What if you plugged in something complicated for x? If I ask you to find g of a minus 3, you'd start off the same way. You'd have g of empty hole equals empty hole squared minus empty hole. And this time you'd put a minus 3's in the empty hole. So as I square this first a minus 3, I get a squared minus 6a plus 9. When I subtract this a minus 3, I get negative a plus 3, because I'm distributing a negative 1 over that second bracket. Combining like terms, I end up with a squared minus 7a plus 12. So you can do some pretty complicated stuff with this new notation. We talked about the importance of being able to put functions together in one problem. This next example does that. We do a computation that has both the function f of x and the function g of x in it. Well, I haven't evaluated f of 4, so I'll say 3 times, and then I'll put a big bracket here for f of 4. Now if I write f with empty holes, it's 2 times empty hole minus 3. And if I want f of 4 here, I have to put a 4 in the empty hole. Now I said that this was not multiplication. This was a single number. This is multiplication. 3 is not part of this. This is a 3 times f of 4. And this is 4 times g of negative 3, but I did g of negative 3 already. I did it right here. So I'll just bring it down. So again, this is 2 times 4 minus 3, which is 5. So that's 15 minus 48, which would be negative 33. So here's an example of how the new notation, you can put different functions together. It looks very simple. It's very simple to work with. But boy, if you didn't have that notation, that would be a complicated problem. Now in the next 2 or 3 sections, we're going to be concentrating on graphing. So let's get started here. Here I've asked you to graph y is the absolute value of x, or f of x is the absolute value of x. Remember, f of x and y are interchangeable. F of x is just the second number in the ordered pair. I need to pick some x values that we're going to graph at, so I'm not going to do a lot. I'll say negative 3, negative 1, 0, 1, and 3. And what we're graphing is y or f of x is the absolute value of x. So the absolute value of negative 3 would be 3. The absolute value of negative 1 is 1. Finish it off like this, and then you have to graph the points. Negative 3, 3 means 3 to the left, 3 up. 3 to the left, 3 up. Negative 1, 1 means 1 to the left, 1 up. 0, 0, of course, is the origin. 1, 1 is 1 to the right, 1 up. And 3, 3 is 3 to the right, 3 up. And there's your graph, kind of a V-shape graph. That's the graph of y as the absolute value of x. Now in the second one, I ask you to graph y as the absolute value of x plus 3. I changed the name a little bit. Since f of x was the absolute value of x, I'm saying the absolute value of x plus 3. Well, that's a little different, so I'm calling it g of x instead of f of x. I'm going to use the same numbers, negative 3, negative 1, 0, 1, and 3. But if x is negative 3, what's x plus 3? Well, negative 3 plus 3 would be 0. If x is negative 1, this would be 2. If x is 0, this would be 3. If x was 1, this would be 1 plus 3, which would be 4. And if x was 3, this would be 6. And g of x is the absolute value of x plus 3, and this is x plus 3. Well, those are positives, so perhaps not the best choices here. Let me pick down here negative 5 and negative 6. And then if x is negative 5, x plus 3 is negative 2. If f is negative 6, this is negative 3. And when I take absolute values, absolute value of x plus 3 is the positive value of x plus 3. So that's 0, 2, 3, 2, 3. The absolute value of negative 2 is 2. Absolute value of negative 3 is 3. Let's see what this graph looks like. When x is negative 3, y is 0, so I plot that here. When x is negative 1, y is 2, so I plot that here. When x is 0, y is 3, plot that here. When x is negative 5, come out over here to 5, y is positive 2, so plot that here. When x is negative 6, y is positive 3. And so here's the graph I get. Now that's kind of interesting. This graph looks the same as the graph above, just moved over 3 units to the left. So it looks like when I added 3 to the x, that shifted the graph over 3 units left. We're going to see some interesting relationships on graphs like that in the coming podcasts. See you next time.